Something really valuable about actually attending and being here in person is having the opportunity to actually ask the speakers while they're there, go up to the microphone, ask a question that you have, or meet them after the talk, chat them up in the hall. There's just a lot of opportunities if something isn't really clear to you to kind of just get in there and get a much clearer answer if you need one.
Hello, everybody, and thank you for joining me for Rvalues and Move Semantics. This talk is part of the Back to Basics track, even though I believe that it serves for, I would say, any level of C++ programmers. It's an important topic, and it's good that you are here. A few words about myself. I'm a lecturer at the Academic College of Tel Aviv and Tel Aviv University, a member of the Israeli ISO C++ national body, co-organizer of the core C++ conference and meetup group, and a trainer and advisor for C++, but not only. Let's start with motivation for Move Semantics. Move Semantics was added in C++ 11. It was a very important addition, and let's understand the reasons why it is there. So let's take the example of a Godzilla. Usually I'm using a Godzilla as an example of a big object that is expensive to copy, okay? So let's assume that we have a factory that can create Godzillas. From the code here, we can assume that the factory is creating a local Godzilla internally and then returning that by value. And then when we get the Godzilla created by the factory back to G1, most probably, or it might be, that it would be copied using the copy constructor, while it might be that maybe we can do it a bit more efficiently. How can we make it a bit more efficiently? Well, the Godzilla that was created inside the factory, the local one, is going to meet the destructor very quickly. At the end of the statement. It's a temporary object. It was created inside the function. So instead of copying it, maybe we could take its assets and tell it not to destruct what it created. It would be more efficient, but can we do that? Let's continue with G2. G2 was created with the empty constructor, then we use the assignment operator, and here, again, the factory is creating a spooky Godzilla, again, a local one, returning it by value. And then again, we use the assignment, and before C++ 11, we just copy. Can we do it more efficiently? Well, maybe we can steal the assets of this temporary Godzilla that was created in the factory. A third example, a third case. Let's assume that we're using standard library list. The standard library containers, all of them, take arguments when we want to push something into the container and copy the argument. So when we push back a Godzilla, this sweetie one, into the list, before C++ 11, probably we are copying the Godzilla that was created on the callee side without any actual need, because we don't need this temporary object anymore. Now, we couldn't take the actual object into the list because the object was created here. Unless, of course, maybe there is some optimization, but let's assume that the compiler was not able to perform any optimization, then there is an object being created on one side, and then the object is passed to another side, but then the other one, which needs the values, maybe it can move, steal, take the values instead of copy them. So this is the motivation. The idea is to avoid redundant copying when we can steal from a dead object. Now, maybe steal doesn't sound so nice, and it is not a dead object because we cannot steal from a dead object. So it's more a move instead of steal, sounds better, I would say, and an almost dead object. An object that is about to be destructed. In some cases, I would say that the compiler is able to perform some optimization called return value optimization, copy elision, or named return value optimization. I will ignore them. Maybe I will discuss them shortly, but not in all cases. So the idea that we can save the need for copying in cases where the compiler was not able to perform any other optimization. Because if the compiler was able to do the optimization, then the need for avoid copying is not there anyhow. But that's not the case always. And we may discuss that later. A few recap questions to see that you are with me. Should we still, move in this case? I mean, still and move is the same. What do you say? I hear no. And the reason is str1 might still be in use. I mean, the next line may use str1. So no, do not move here. What about this one? So when we concatenate two strings, we get back a new string, which is just created for us, which is local, which is going to die in a moment. It's a temporary. Can we steal it? Yes, we can. Should we? Yes, we should. Okay. So the question is, how can we distinguish between the two? I mean, in the first case, we do not want to move. In the second case, we do want. What is the difference? How can we tell, oh, this one is that and the other one? So let's start with the compiler is able to distinguish between the two. So if you get the help from the compiler saying, oh, I'm the compiler, one of the things that the compiler is good at is following lifetime. And the compiler can say, oh, I see that this object lifetime is ended by the end of the statement, and the other one is not, okay? So we need some kind of help from the compiler, but let's start with terms. Let's have different terms for each of these. So let's see the differences and the similarities. Both assigned expressions are references. I mean, the second one is the local reference to a temporary. But there is an object living there for a moment. So both are references to an expression. Currently, both lines would call the copy constructor. When I say currently, I mean before C++11, or if we do not implement the proper operation to allow the second one to be more efficient. And there are kind of different references. The first one would still be alive after the end of the statement, and the other one would not. By the way, temporary object was a term being used before C+11. C+98 already used the term temporary object. So let's name them. Let's call the one that would still be alive an Lvalue reference. Now, the name Lvalue reference comes because it may sit on the left value of an expression. It might be assigned to. I mean, you are still alive. You have an address. I can assign something to you. So you are a valid Lvalue. So let's call you Lvalue reference. Does it mean that you will be always on the left value of an expression of a statement? No. You can be on the right side of a statement and still you are an Lvalue reference. Can you give me an example of an Lvalue which sits on the right side of a statement? This one, SL1, is an Lvalue. It is on the right side. It is still an Lvalue because it would still be alive after this statement. So the name Lvalue doesn't mean that you should always be on the left side. It means that you can be on the left side, which means that you would be still alive. Okay, so this is the nickname for these kind of references. What should be the name for the other one? I mean, what is the opposite of left value reference? I think we can go with the opposite of left is right. So let's call it Rvalue reference. Which means that it doesn't mean that you necessarily have to be on the right side of an expression. I mean, you can be sent to a function. Would we consider it as a Rvalue reference? Yeah, if you are temporary. A question, can an Rvalue reference, something which is a temporary, sit on the left value of a statement? Because if the answer is yes, then we can wrap up and go. I mean, so what do these names say? And the answer is Yes, it can. An R-value reference can sit on the left side. Can you give me an example? I will give you an example. If we are using vector of Booleans, and we use the subscript operator, we take the index 0 of this Boolean vector. We get back not the actual Boolean by reference that sits on the 0 index, but a proxy to this one, because Booleans in a vector of Booleans are sitting in bits, and you cannot return a bit by ref, so the language implemented the return value from a bool of vector, from a vector of bools, when you ask for the index, to return a proxy object. And the proxy is returned as a local variable created when you call the subscript operator. So this one is a proxy, this one is a temporary, this one is an R-value sitting on the left value of an expression. So it is just a nickname. I mean, R-value can sit on the left value except for primitive types. If you're a primitive type, if you're an int, and a temporary int like 3 cannot be assigned with 4. 3 cannot be assigned also with 3. So 3 cannot be on the left side of an expression, but some object can. And the example was the return value from vector of Booleans subscript. Anyhow, this is the name, okay? It is just a name. So we have L-value reference and R-value reference. Now we need a language symbol to distinguish between the two. So for the first one, we already have what is the reference symbol for a left value, a L-value reference? The ampersand, okay? We use it, we know that. It's not new. We need another symbol, so the compiler can help us distinguish between the two for the R-value reference type. So they thought which symbol is not used enough in the language, something that is quite rare. Let's use something like ampersand. Oh no, ampersand was for the first one. So double ampersand. Okay, let's have double ampersand as the symbol for R-value reference. A reference to an object that the compiler sees that this object is going to die at the end of the statement, that this object is temporary. Okay, so we can distinguish between the two. So what can we do with that now? I mean, yeah, we have two different types. The compiler actually knows the types because the compiler is following lifetime. So what can we do with that? And the answer is functions overloading. We can create two functions, one that would deal with the one, like with L-value references, and the other with the other, and then we can distinguish between the one in cases that, oh, okay, we need to do something with an object, like copy it. The one that would get L-value reference would actually copy. The one that takes the R-value reference would steal, oh, sorry, move. Okay, that's the direction. That is what we try to achieve. So let's have a toy example. We have two full functions. The first is taking an int as an L-value reference. The other is taking an int as an R-value reference. And they are just printing for this example. In main, we create int I equals 3, and we send I to foo. Which foo would be called? We send I, and the foo that would be called is the first one, right? I is a variable that is still alive, would be still alive. It's an L-value reference. We'll call their first one. What about foo of 3? I mean, foo of 3, is it valid? 3 is not an actual reference. Can we send 3 to something that expects a reference to an int? You know the answer. The answer is yes, we can, and this is the case since C+98, because we can send an int, like 3, a value, to a reference since C+98 if you expect to get it as a const reference. A const reference can take a value, and then there is a temporary object or temporary variable being created, and we actually get a reference to the temporary. So here again, the 3 would create an int. Oh, we have an int. Does this int have a reference? Yeah, for this point of time. Yeah, the compiler would treat it as, yeah, I created an int for you. And then this int is a temporary, is an R value. And we will go to the second one. What about j? J is a constant j that takes the value of I. To which of the two j will go? foo of j? That's a tricky question, because the answer is not in the slide. It will be a compilation error. The compiler will not be willing to send j to either one. I mean, the one that takes Lvalue reference say, I may change the int that I get. No, I'm not allowed to be changed, I'm const. The one that get Rvalue reference is even worse. It is saying I can change you, but I can also steal you. I mean, there is a rumor that somebody got to that function and lost a kidney. I don't know, don't go there if you still want to be used after, okay? It is only for somebody who is on his last statement. And J, even though this is the last line of the function, the compiler doesn't treat the last line of the function unless it is the return statement, which has another rule that we will discuss. The last line is not something special. J is still alive. J may be still used. So J cannot be sent to the Lvalue reference. It cannot be sent to the Rvalue reference. It could have been sent to a... There are two more. There are four options in the end, which are Lvalue reference, Rvalue reference, and the const versions of both. Const Lvalue, const Rvalue. So J would be able to go to the const Lvalue reference. But we don't have that here. So J would be compilation error here. You cannot send foo j to any of those. Okay, we got it. I think that we're ready for an exercise. So the classic exercise is to implement string. Now, string, let's discuss string. When we copy a string, should we get a string in order to copy it to another one. Should we always copy? No, we saw an example. In some cases, we can steal the string. I mean, you got a string. Maybe we should not copy you. Maybe we can take your assets. When I say take your assets, it means that we can take the internal pointer that points to the char array, right? Take the pointer, what we call shallow copy, take the size, and ask the other one not to free this allocation. And since the other one, this is relevant, of course, only if the other one is an Rvalue. Since the other one is not being used anymore, that's valid. This is what we aim for. So I think we have time to do that together. Let's try doing it together. We have the solution, but let's start with the skeleton. So we have a MyString already prepared, but this is the pre-C++11 version without the move operations. So the string has a size, the string has the char star, which is being allocated. I have a private constructor to accommodate all cases of I do have a size already from somewhere, like in the copy constructor. I don't still have a size. Okay, if you don't have a size, so you can calculate the size and then call by delegation the private constructor. So I have a constructor which takes char star and calls the private constructor. By the way, I'm using here memcopy. I could have used stud copy. Anyhow, memcopy is fine here because it is only chars, and I prefer that over str copy because I actually know size. I don't have to loop and ask, are you on the null PTR? But that's just a little implementation detail. So we have the destructor. We have a copy constructor, which actually copies. Maybe you cannot see it here, but once I call the other private constructor, I go to the constructor that allocates and copies. So I have a copy constructor and I have a copy assignment. Do you remember that in the copy assignment you have to check for self-assignment to avoid the case of, oh, it was me, and I just deleted without noting that it was me. And when I come to copy, I realize that, oh, there was a string there. What happened? Oh, I just deleted it, but it was me. So I just checked before. Yeah, you know that. That's okay. We have a to-do. We want a move constructor and move assignment. So let's just check where, in our case, the move operations might be used. I mean, we have in the main few things. We have a call to foo. And the call to foo gets back an hello that is converted to a string. The string might be copied here. Well, not so, because there is copy elision optimization. So we actually don't see any copy constructor here. And if we do not see any copy constructor, we just see the hello being created, and that's it, and being printed with the char star constructor. No copy constructor. How come? compiler optimization. So if there is a compiler optimization, we will not see the move operation either, okay? We will have to play with that in order to make the move come into life. But we would see the move here on S3 equals by. So let's try to understand what happens here. The assignment operator is expecting another MyString. And this one is not a MyString object. So the compiler is tempted to give compilation error, but then the compiler recalls that, oh, maybe I can do a conversion, do a casting. Yeah, I can convert char star to MyString because there is a constructor in MyString which is not explicit. So MyString is being created here. We'll see it somewhere here. This is this line. We created the by for the right side. And then we call the copy assignment in order to copy the newly created object on that side into S3. Should we actually copy? I mean, when we copy, we add by on this address. And now we will have by on another address because it was copied to another location. And the old one that was local, that was temporary, that was this one, would just be distracted. Can we do it in a more efficient way? Yes, this is the place where we want to move. We can take this one that is created and being distracted at the same line and just take the allocation and ask the by, don't say by, I mean say by, but do not deallocate the by. Okay, so let's do it. You will help me. It is always fun to do live coding. In some cases it works. Okay, this is the to-do. What did we want to do? Implement two functions, right? I will start with copy-paste. Why? I don't know why. So I'm copying, pasting the copy constructor and assignment operator, and I'm starting to change them. I remove the const, and I will explain why I remove the const. The move constructor wants to take an Rvalue and steal it, move it. But in order to move it, I need one more thing. I need to ask the other guy, I need to ask the other object, please do not deallocate. And for that, I need to write something. I need to put null PTR in its current pointer. So it cannot work with the const. Now, don't worry. Usually, our values are not const. Usually, our values are created as, oh, I call a function, I got by value. Or I have some, the by that I see below. Usually, the R values are not const. But if it is const, you cannot steal it. Sorry. Okay, so we have the MyString as an R value. And what do we want to do? Well, the thing that we want to do is to copy the size, right? Then copy str as a shallow copy, right? As a shallow copy. Then maybe say that we are in the move constructor. Then not forget the Noexcept that we may discuss later. And then one thing that we should not forget is to zero this one. Now, one may ask for another thing to zero also the size. That's a question. Maybe for consistency. So yeah, for consistency, I will zero the size as well, but I could live with a size which is not correspondence to the, no, because if it is null PTR, you should avoid asking the size, but let's do both. Okay, let's go now to the other one. Again, no const. This would be the move assignment. So the idea is move constructor would be able to move when we create a new object from a temporary. Move assignment would be able to assign when we assign from a temporary like the by that was in main. So we actually do not need the check for self-assignment. Why don't we need the check for self-assignment? Because usually you cannot assign yourself as an R value. I mean, you are not an R value. You can do that if you write an intentional bug. And if this is the case, that was an intentional bug. I want to let you write your own bugs, but this is not something that should happen in a real program. So I just move it away. I should distract my old allocation. Yes, I should. But I will not do that because I'm going to do something a bit different. What I'm going to do, and I'm not going to mem copy, and I'm not going to, what I'm going to do is to swap my assets with the other one, with the other guy. I'm going to say, you know what? I'll give you my size, and you'll give me yours, and let's do the same for the string, right? And I think that this should be fine. Maybe I will print right after. And instead of copy assignment, let's say that we're in move assignment. Okay? Oh, I can do that before because I'm actually printing my old value and then the value that I'm going to take. So yeah, maybe I can do it here, which is, oh, this was my old value, and I'm going to take the other one. And then I do the actual thing. Why std swap works well here? Because once I trade mine with yours, you're going to die in a moment, right? Can you please destruct my string? I don't need it anymore. Why? Because I took yours. Sounds reasonable. Sounds fair. So I give you mine, I take yours, and you will take care of destructing mine. I'm running with fsanitize address to make sure that I do not forget any deallocation. I hope I don't. And I want to run it. And I want to see, do you remember that that was a call to the copy constructor? I want to see if now we'll see a call to the move constructor. Let's do it. Okay, so happily it compiles. And we see, oh, yeah, we actually call the move. That's good. And we can see that the buy was allocated at this address. See the 70 at the end? Before that, I had the 50. When buy dies, it no longer holds buy. It holds my old allocation of a single character containing the binary 0, backslash 0. And I actually took the original buy. Yeah, that is what we wanted. Yeah, we achieved that. That's nice. But we still don't see the call to the move constructor. And I'm a bit frustrated about that. I want to play a bit with, maybe we can make it call the move constructor. Now, in order to call the move constructor, I want, in a way, to eliminate the optimization that the compiler is performing here. So there is a flag saying, compiler, can you please eliminate constructor elision? And the flag is f no elide constructors. I hope I write it correctly. It would not help, but we can check. Okay, so with minus f no elide constructors, I see the same. The copy here, by the way, is the copy at line 60. This is an actual copy, right? But I don't see the copy of line 57 because, do you know the reason? The minus f no elide constructors doesn't get into effect here because we are in C++20. Since C++17, copy elision of direct object creation is mandatory. So the compiler is not allowed not to perform this optimization. The compiler say, I hear you, but sorry, I'm obliged to this optimization. So what can we do? Go back to 14. Yeah, we can try that. Okay, so let's try with 14. I hope that they didn't use any. Yeah, now we are with, oh, you do see the move. And then you see destructor, because the hello that is created here is actually created now. And then you see the move again here. Now the compiler was able to do the RVO, copy elision. Of course, in production, I don't want this flag. Without this flag, even in 14, which is not a mandatory optimization, you will get this optimization. But not always. When I say not always, let's go back to 20. And I do want to play with this function in order to show you that, yeah, move constructor and move assignment are important because in toy examples, in some cases you say, oh, I would get RVO anyhow. But in real programs, the compiler is not able always to do that. So in order to make it not an RVO, but an NRVO is named return value optimization, let's give this string a name. So we'll call it S, and we'll put a low in S. Okay? And we'll return S. So now, do you think that we'll confuse the compiler? What do you say? No, the compiler is smarter than that. Now it has a name. Would it change something? No, it will not. It will not. But by the way, I think that if I would say minus no allied constructors now it is not a mandatory optimization, so maybe this flag would have an effect. And it does. Because the compiler says, yeah, I can perform the named return value optimization, but you told me not to, and this is not a mandatory optimization, even in CppCon, so I will not, because you asked to. But that's with the flag. I want to perform something without the flag to show real program. So let's move that, and we're back to, oh, there was a compiler optimization. What can we do to avoid this compiler optimization? In this case, this is not a mandatory, but yeah, the compiler can see that instead of actually creating the object in the function, I can create the object on the return value. And the caller asks the return value to be created directly on S1. So S1 is created with a value directly, immediately. So in order to avoid that, we can do something like that. Let's have two, S1 and S2. Okay, let's confuse the compiler. I mean, let's make it not be able to decide if rand modulo 2, then return S1, else return S2. I hope that this will help. Okay, so this is like a real program. We're branching, okay? We don't know which actual string would be created. Now, the compiler can do an optimization of assuming that one of them will be created, then creating the one on the return value. Then if it needs the other one, it can then override it with the actual, might be. But eventually, I can track an action where, oh, you did have to move because you didn't know which one should be created, and it is still a local variable. So it is still an R value. It's not an L value. So I can still take it into the move constructor. Let's see. And yeah, we got to the move constructor only once here because one of the optimizations was performed, but the one inside the function couldn't be performed. That's nice. That's a real program. I mean, in real programs, we have branching. Okay, let's go back to the slides. This was the exercise. Good exercise, guys. Let's talk about reference overload resolution. How the compiler knows where to go because it has this table. If I'm calling with an L value and I have all 4 options, I will prefer, my first preference would be the row number 1. If I'm on column A, I'm an L value, I will go to, the first choice would be column 1, row 1, sorry. But I can go also to row number 2. I can be accommodated into the one that gets a const L value reference. And we know this rule. This comes from CpplusPlus. It's not new. But I cannot go to the move options. Why? Because someone lost a kidney there, and you don't want to be moved from if you are an L value. Let's go to column B. In column B, I'm a const L value. If you're in const L value, you have only one choice. You can go only to row number 2. You can see, by the way, that row number 2 is the most universal one. It takes all of them. By the way, the copy constructor is the signature similar to row number 2. If you're an R value, you can actually go to 3 options. The 4th one is not really relevant. Usually, we will not implement the 4th one. Why? You will not see the 4th one in real code because there isn't much to do with a const R value. You cannot actually steal it because in order to steal, you have to put null PTR in its assets or to avoid the destruction of the assets. So 4 would not be created. By the way, if you ask yourself, are there any cases where I would implement number 4? So there is a question in Stack Overflow. And the person who is usually answering quite fastly questions on R value and move semantics in Stack Overflow is the man behind R value and move semantics, Howard Inant. So if you ask a question on R value and move semantics, you may get an answer by Howard Inant, who invented this. That's good, that's nice. And there is a question in Stack Overflow. So R value would usually go to either row number 3 or row number 2, depending on whether you have row number 3. I mean, if I implemented the move constructor, I will go to the move constructor. But if not, there is a fallback. OK, the fallback is you can still use the copy constructor. Yeah, copy constructor can copy even if you're an Rvalue, because Rvalue can go into row number 2. The fourth option is also quite real. I mean, usually we control the creation of Rvalues. And we will try to avoid creation of Rvalues which are const. But if you're const, you will not be able to go to row number 3. This is quite real. By the way, this table is taken from Stack Overflow. You can find it there. I will post the slides, and you can see the link. Some additional rules. If it has a name, let's go to bar. Bar takes an Rvalue called I, and then bar calls foo. Which foo would be called? I'm sending 3. I'm coming to bar. With 3, yeah, 3 is a valid Rvalue. It creates a temporary int. I come to foo. I come to bar. Then bar calls foo. Which foo would be called? I mean, I was passed as an Rvalue. I got I as an Rvalue. And the foo that would be called is the Lvalue1. Why the Lvalue1? Because once I have a name, and I has a name inside bar, then the expression that holds this name is an Lvalue. And there is a reason behind that, because yeah, I can use I later on in the same function. I mean, bar would be able to use I. So if I would send I to a function that takes it as an Rvalue, it might be stolen, and then I cannot use it later. So, but if I do want to call the Rvalue case, then move it. And there is a function called studMove. studMove asks the compiler, can you please cast this thing to an Rvalue? Because I want to reach the Rvalue version. And this is the reason for studMove, because in some cases, yeah, but I want you to be an Rvalue. So I cast you to an Rvalue. So studMove is a casting to Rvalue reference, preserving const volatile. If you were const, you will still be const. If you're volatile, you will still be volatile. stdmove doesn't move. Scott Meyer's modern C++ book. It prepares you to be able to move. But it doesn't actually move, it just casts. Okay? The thing that actually moves, like in this line, is not the call to studMove. The call to studMove allows you to move. The actual move is the call to, don't say assignment, it's a copy constructor, to the copy constructor. We create a string, we call the copy constructor. Sorry, we call here the move constructor, because we use studMove. If we wouldn't use studMove, then we would have called the copy constructor. So we call the move constructor because of the studMove. A question. Okay, are you ready? Let's see that we recap that. Is it valid to use studMove on an Lvalue reference? I mean, studMove casts you to an Rvalue. The case that we saw before is you were an Rvalue, but now you have a name, so the expression that relates to you is an Lvalue. But I know that you were an Rvalue, so I feel okay using studMove. Would it be fine to use studMove on something that is an Lvalue? Or maybe it would be compilation error, or a runtime error, a linker error, a warning, or maybe it is fine. What do you say? Well, it may compile, and in some cases it is valid. Yeah. So these are the answers. And the actual answer is yes, it is legit in some cases. Can you give me an example where I get an Lvalue and I want to steal from it, even though it is an Lvalue? Why do you steal from an Lvalue? Somebody else is looking at that from the caller side. Why do you steal from it? Can you have an example? A library function, quite known, quite useful, used in sorting, for example. Swap. Swap in C11 is implementing using move. I don't want to copy into temp. I can steal. And I still can use LHV in the next line by assigning to it the other value. I don't need the old value because I'm going to override it with a new value. So why should I copy? Anyhow, the old value is going to be overridden, so why to copy? You can move. So let's move. It would be much more efficient. Now, even before C11, for the internal types, there was another implementation of swap that did that efficiently, like, for example, for a vector. But for your own types, no, if you go to swap before C++11, you actually copy the Godzilla. If you swap between two Godzillas. Should I copy the Godzillas? No, you can do a tripod stealing move. Okay, so this is the proper implementation. And yeah, we move from an L value, but don't do that unless you're going to override it with another value, because otherwise the caller who provided the object would get an object that was moved from. No, here it is okay, because I gave you something else, I swapped. The rule of implicit move on return, when you return a local, then there is an implicit move on return. No need to do std move. In fact, calling std move on that is a pessimization. I will not, maybe let's explain why it is pessimization, because once you do call std move on something that would have been moved anyhow by the compiler, you lose the optimization of copy elision. So the first preference is, can I not move and not copy, just take the object and create it on the other side? That's the best thing, copy elision. Why? Once you say std move on the return value, you omit the option for copy elision, and I want copy elision. When I say, okay, if compiler, please, if you can give me copy elision, I prefer that. But if not, I want to move, that would be the case anyhow, because local variables on the return are implicitly moved. It means that I can return something which does not, which blocked, which deleted its copy constructor. Can you give me an example of an object that deleted its copy constructor and I could still return it and get it by value? Unique PTR, for example. Unique pointer, unique PTR. Unique PTR doesn't have a copy. It implemented move. I can return unique PTR by value if it is a local variable, and it would be moved automatically, implicit move on return. This is the rule. So when do we need to implement move? We need to implement the move in cases where there is a reason for move. Does this class need a move? No, there is nothing to move. I mean, X and Y should be copied. I cannot move X and Y. I can move pointers. I can move resources. So no need for move. What about this one? I mean, this one is a string, and string does have allocations. But the basic object-oriented rule is everyone for himself, right? The misanthropic rule. String takes care of itself. I don't need to take care of how string works. So no need for move. String would, there is a default move for the class. So we prefer to go with the rule of zero. Rule of zero says, if you didn't implement any of the 5, destructor, copy constructor, assignment operator, move constructor, move assignment, you didn't implement any of the 5, you get the default for the 5. And the defaults are performing member-wise operations. So I perform member-wise move on my members. That's good. This is what I wanted, and on my base class. Yeah, that should be your aspiration. Not in life. In life, you can have additional aspirations, but in coding your classes. What about this class? Oh, here I do have allocation. Oh, so you need to take care of the actual thing. But then, I have here 2 solutions. I would not have time to go through that, but what should be the right way to implement that thing to isolate the resource management from all the rest? Do not do these 2 things in the same class, business logic and resource management. Take the resource management, create a separate class. Do the move operations there. Use it in the business logic class. That would be following the rule of zero. Isolation, decoupling, reusability. So take this class, break it into, I have an array without a name. And this array takes care of the move operations on the allocation of the int star. And oh, you also need a name, so let's have another class named array that would take the member array and a member for name. And that class, the other one, would use the rule of zero. And this is the second solution here, but I would have to skip that. Rule of 3. Rule of 3 is quite old. Rule of 3 is C+11. Rule of 3 says, implementing any of the 3, destructor, copy constructor, assignment operator, wait, this part is new, C++11. Before that, in C++98, it said, then you should consider or you should implement the others. Since C++11, it says, if you will use or try to use the compiler defaulted implementation of copy constructor, you will get a warning, depending on the compiler, but the spec says that it is deprecated. I mean, you implemented the destructor, so you don't have a copy constructor. I mean, you do have it for backward compatibility, but you will get a warning. What should you do? Either implement it, or declare it with a default, or block it. So the best thing is, once you implement the destructor immediately, not tomorrow, not next week, not a to-do comment, immediately. Block the copy and the assignment, but that is all. That is Scott Meyer's effective C++, I think. Rule of 5 is talking about what happens if we declare any one of the 5. If you declare any one of the 5, you lose the default move operations. But if I like the default move operations, let's assume that I declared or I implemented the destructor only for some printing to the log. Or maybe I declared the destructor because I needed the virtual destructor. But I do want the move operations, the default ones, so just declare them with equals default for all the 4. Also for the copy and assignment. And if you declare any of the move operations, the move constructor or the move assignment, then you implicitly delete the default provided others, copy constructor, assignment operator. So you have to take that into account, and again, you can bring them back with equals default. When do we use Rvalue ref? So mostly on parameters to allow the overload move operations, in very rare cases on variable definition, and in really very rare cases on return value. It is quite wrong to say that the function returns an Rvalue reference because usually it will be a dangling reference. If I say by value, it means that the compiler takes care of, yeah, the other side actually holds something. If I say Rvalue, I'm saying, okay, I'm returning a reference of something that is dead. Oh, that's not a good idea. Then comes the question, do we have any example of a function that actually uses return of Rvalue on the signature? And this question appears in Stack Overflow, and there's an answer by Howard Inant. By the way, do you have an example? You know one function like that. StudMove. StudMove itself is the example. StudMove actually returns an Rvalue, but that's a special case because we know that the thing that we move is still usable on the same statement. So StudMove is a very special example, but usually, no, I don't want functions that say that they return Rvalue on the signature. A few words about move if Noexcept. If you remember, I added Noexcept on the move operations. There is a reason for that. The story is going like that. I would do it quite quickly. Let's assume that I have a vector, and the vector is the vector capacity is exhausted. I push back. There isn't any space for the vector capacity, so I need to create a new allocation. What should I do with the currently available items that are in the old allocation? Should I copy them or move them? Now, copy is simple, but I can move. I don't need them in the previous place. The problem is, if I start moving them, and then one of the move calls throws an exception, I now have a zombie case on both sides. I mean, this old allocation just, lost a few of its items. The other one has the items that were able to move, but it doesn't have the others that did not, because there was an exception in the middle. So I can come back to the user and say, we had a problem, we didn't succeed in pushback. I throw an exception. And the user says, okay, you didn't succeed. Can I still use the old vector? No, sorry, I just ruined your vector. No, that's not good. So the spec says that calling pushback or having to reallocate, resize, reallocate, create capacity, reserve, like for calling reserve, and reallocating would use move only if move says that it is Noexcept. And I will not run that, but I can tell you that you can actually check that. If you have one with Noexcept and another one without, and you check it, you will see that one calls move constructor when you do pushbacks, and the other is calling copy constructor on the items that need to be moved or copied from the old location to the new location. Don't forget the Noexcept on your move functions. Let's go forward to forwarding references. Haven't we suffered enough? No, there is something more. So it was called universal reference back then by Scott Myers. Now, usually it is called forwarding reference. It is the same thing. When we use double ampersand on a template argument, it is not an Rvalue. We are in C++. There is a rule behind that. It goes to reference collapsing. Anyhow, do you see the double ref here? The double ref here is not an Rvalue because it's on a direct template argument. It means T is a forwarding reference, which means it might be an Rvalue, but it might also be an Lvalue. How can I tell? You can ask it. And you can also use std forward, and std forward, as opposed to std move, that it casts to Rvalue, std forward conditionally casts to Rvalue, only if you were Rvalue to begin with. I mean, I want to get you back to be an Rvalue, but only if I got you as an Rvalue. But if you went in as an Lvalue, because this is how it works, then I want to keep you as an Lvalue when I forward you, when I pass you to another function. So here, bar says, I got this one. And foo says, oh, when I call foo, I don't want to cast you to an Rvalue if you were not an Rvalue. So I use stood forward and not stood move. Let's see two usage examples of forwarding reference. One, I have a class array. In the array, let's assume that I have an C-style array, and I want to implement emplace. Now, emplace takes variadic pack of Rvalue reference, of forwarding reference arguments. Why? Because some of the arguments will be Rvalues, other would be Lvalues. I don't know, I don't really know. And I want to forward these arguments to the constructor of T that is going to be called here with placement new. Put aside the placement new. If you know that, you can understand why I use here placement new. I actually call the destructor on the old object that was there, and then I create in place the new object using the constructor, but I want to forward to the constructor the values or the objects that I got using their original reference type, be it Lvalue or Rvalue. So I'm using stood forward for that. Another example, I want to loop over a vector of something, and I want a generic function that we'll call reset. Reset will reset the entire vector. So in order to make it generic enough, I loop with double ref. Why do you loop with double ref? Because double ref can take both Lvalue cases and Rvalue cases. Now, most cases will be Lvalue. When do we get an Rvalue when we loop over a vector in a very specific case? Vector of Booleans. And we can still write into this Rvalue. That's the proxy case. So in order to, if you want to implement a loop that would accommodate any type of vector, including vector of Booleans, and you want to do something with the values to write to them, then you should take it as a forwarding reference, and then you can accommodate both the Lvalue case, which is the generic case, in the Rvalue case, which is the proxy for the vector of Booleans. Let's do the quiz part. We have time. It will be quite quick, but let's start. Let's try that. What's wrong here? I want to implement a push function in a stack. And in the stack, I'm taking, is it a forwarding reference or an Rvalue reference? What do you say? So it is complicated. It is a bit not so simple. This one is not a forwarding reference. It is an Rvalue reference. Why? Because T is being deduced as part of the class, as part of, oh, I created a stack of T's, a stack of ints. So when you call push, T is deduced already. So it is like saying int double ref. It's not saying something which is templated. I mean, T was deduced already. So it is not considered a forwarding reference. So the question is, what's the problem here? And the answers are, T double ref push is not a forwarding reference, thus compilation error. Or T double ref push is not a forwarding reference, thus we support only push of Rvalues. Or C, push may add to the vector a dangling ref. Or D, push may inefficiently copy. What do you say? Shout out. So it is B, we actually can use this function, but only with Rvalues. This stack cannot take Lvalues. Oh, you do want to take Lvalues? So implement another push. So there are two options how to do that. You can actually implement two pushes. One for the Rvalue case and another for the Lvalue case. You see that I'm actually using move here because I know that you are an Rvalue. It's not a forwarding reference. And another option is to actually use another template argument. This template parameter u is being used here. I actually narrows it. I check that it is convertible to t. And inside I do use stood forward because now it is a forwarding reference. Okay, another one. What's wrong here? I'm trying to pop from the stack. I want to pop from the stack, okay? So I call pop back. I take first the reference. Now, back doesn't remove the item from the vector. So I call back, I take the reference, then I call pop back, then I stood move. And the answers are pop returns a dangling reference, or pop moves from a dangling reference, or pop as an undefined behavior, or the reference is being invalidated once we call pop back. I mean, this is not good. We can rewrite it. We'll do it in a minute. And the answer is D. When we call pop back, the actual value is invalidated. There is a call to the destructor on that value. So we hold the reference to a value to an object that was invalidated, which destructor was called. And then we move from it. No, it is dead by now. No, you should do it differently. I mean, if we were before C+11, we would just copy it out. I don't want to copy it out. I want to move it out. I don't need it in the vector anymore. I just pop it. So the right way to do it is to move into a local variable, then to pop back, then to return E. Now, when I return E, I actually either using copy elision or moving out based on implicit move on return. So this is a more efficient way than just copying the call to stood move here is important for efficiency. Let's summarize. Are you ready? Okay. Our values and new semantics are here to improve our code performance. Stick to rule of 0 when you can. Even if you use rule of 0, your code is more efficient than if you are before C+11, because you get the default move operations on the strings, on the vectors, on the hash maps, on the containers that you hold. If your class do manage resources, isolate it. Do not do resource management together with business logic. Why? Just because of regular design practices. I mean, isolation, decoupling, I want reusability. I want to use something and then use it. And then when I use it, I go with rule of 0, because the class already manages itself. Don't stood move anything without thinking. Oh, there is a call to stood move. Why? Should we? Is it okay? Do not stood move local variables on return because it is specification. Do not move something that is still in use. Even if it was Rvalue, yeah, but you're using it as a name, and you're using it 2 lines below, and the compiler may warn you, static code analysis tools may warn you, but it's not compilation error, and it's wrong because you're still using it. Do not move something twice for the same reason. Don't wave stood move when needed, because then you hurt performance. Like the example that we had with the pop from a stack. If I pop from a stack, I can move the value because I don't need it in the stack anymore. Why not move it out? Yeah, I can. I mean, in many cases, we forget to move when we can. This is your responsibility. Oh, should I move here? Let's do that. Remember that forwarding references need to use stood forward and not move, because if I move from a forwarding reference, I may move from an Lvalue and still use it from the caller side. That's it. That is all what I had. And I still have some time to discuss questions if you come here, because I'm not sure that I will be able to take questions. There isn't much time. So thank you very much. We conclude.